We present DiFaReli, Diffusion Face Relighting. Given an input face image, our goal is to relight the input face under different lighting conditions. One of the hardest, unsolved challenges lies in handling non-diffuse effects, such as cast shadows or highlights, which usually require precise estimation of geometry, lighting, and surface properties. To solve this, many existing approaches require multiple images of the same person taken under different lighting conditions for training their pipeline. This involves setting up costly capture rigs, such as LightStage, or one light at a time capturing. Another approach is to rely on synthetic rendering. However, lab-captured face images or synthetic rendering can look very different from in the wild images, often leading to unnatural results when tested in real-world scenarios. Prior techniques also rely on accurate estimation of geometry, albedo, and light or shading information to relight an input image. However, correctly estimating these factors from a real-world image is extremely challenging. Here, the method fails to correctly estimate a clean albedo and leaves cast shadows in it, which incorrectly show up in the relit result. Relighting the ears and hair correctly also require good 3D reconstruction, but this is very far from solved given a single view input. In contrast, our solution bypasses the need for accurate intrinsic decomposition, requires only 2D images to train, and can solve highly challenging scenarios such as cast shadows, highlights, and unusual makeup. The general idea of our method is to encode an input image into a feature vector that disentangles the lighting information from other information about the input image. This would allow us to modify the lighting in the feature vector and decode it to obtain a relit image. To achieve this, we use an off-the-shelf estimator called DECA to encode an input image into a feature vector that captures the lighting information, along with 3D face geometry and head pose. And we use a diffusion implicit model conditioned on the modified vector as the decoder to output a relit image. At relighting time, instead of starting from a Gaussian noise map, we use an inverted noise map from reversing the DDIM generation process of the input. To help improve details and preserve identity, our feature vector also contains a face embedding from a face recognition model, ArcFace. With this framework, we found that the relighting quality is sometimes poor and does not respect the new lighting information. So, instead of directly conditioning the diffusion model with 27-dimensional spherical harmonics coefficients from DECA, which can be hard for the diffusion model to use, we use the lighting and geometry estimates from DECA to render a shading reference, whose intensities directly correlate with the output RGBs and are easier to use by the model. Then, we pass the shading reference into a modulator network, which has the same architecture as the first half of our DDIM's UNet. The output from each layer of the modulator will be used to spatially modulate the corresponding layer in the DDIM. Here we relight an input image from FFHQ to match the target lighting given by a reference image. Here's the animated result and its shading reference. Our method also works with facial accessories such as sunglasses. Notice that our method can realistically change, add, or remove highlights and cast shadows in the input images. Compared to the baselines, our method produces more photorealistic results and can handle highlights and cast shadows, while the baselines leave residual shadows in the relit images, leading to unnatural outputs. Here are more results. Here we rotate the target lighting around. Notice that our method works across different head poses, hairstyles, facial accessories, and lighting environments. We evaluate our method by relighting each input image to the target lighting and compare the result to the ground truth in multi-pi dataset, shown on the rightmost column. We also test on a scenario where the target lighting comes from a different person. Note that our method can relight not only the face, but the neck, ears, and hair, and can fully remove cast shadows from the nose, unlike the baselines, which leave behind shadow residues, especially for unseen subjects. We compute SSIM, MSE, and LPIPS between our results and the ground truth, and our method outperforms the baselines across both scenarios on all metrics. We test the effectiveness of our modulator and spatial conditioning technique through an ablation study. The result shows that our method better matches the target lighting and produces fewer artifacts. Moreover, our method can change the strength of cast shadows and make these faces look more diffuse or harsher. To summarize, we propose a state-of-the-art framework which solves relighting uses a conditional DDIM and off-the-shelf estimators. This framework requires only 2D images to train and doesn't need any relit pairs, lighting, or 3D ground truth. We propose a spatial conditioning technique to condition our diffusion model with a pixel-aligned shading reference, which effectively conveys the lighting information. Our method bypasses the need for accurate intrinsic decomposition yet can solve highly challenging scenarios such as cast shadows and highlights. Thank you for your interest in DiFaReli. Please visit our website for access to code and more interactive results.